move this out of the way. All right, so we're good with that one. That one should be fine. I'll go back to the page here, and I'm going to go to the next one. All right, so here, let's go. Oops. Oh my goodness, what am I doing? All right, so question 17. So it's saying which of the following statements is correct, and so we got a couple different things here. One way we could check it is we could punch the stuff into a calculator and see if it comes out to the right answer, like if the left equals the right. If it does, then it is correct. There's only one that's right. If you remember back to Math 10C, we learned the exponent rules, and so like for how to combine exponents, we couldn't do it when there's addition or subtraction, right? It was only for like multiplication and division and doing an exponent of an exponent. And basically it was that if you had some base and raised to some power, and you multiplied it by that same base to another power, we could add the two powers, right? So if we had x squared times x to the 5, we get x to the plus 5, which is x to the 7. Okay, so we found we could do that. The same thing works with if the exponents are negative, that's fine. It's just going to be you're counting backwards, right? So just like we did for regular adding and subtracting positive and negative numbers, they're always going to be single digit numbers, so it basically ends up being addition of single digit numbers. So that shouldn't be hard. The other rule we had is, so if you divide, so say I had x to the 6 divided by x to the 2, then I can subtract the exponents, because like division is related to subtraction, multiplication is related to addition. So if we have this 6, it'd be 6 minus 2, and we'd get x to the 4. Okay, and so when we look at these, we should be able to pick out which one is true. We can't add things together like that or subtract things together like that. We can only do those rules when we multiply or divide, and there's only one of those ones that's right. Okay. Anyone have any questions about the exponent rules?
No.
The other one that sometimes people get confused on is if we had an exponent, like something that was already a power, and then we raised it to another power. So say we had x cubed raised to the 5th. And what that means, when you raise something to a power, it means you're multiplying it by itself that many times. And if we looked at this, x cubed means x times x times x. And this stuff to the power 5 means this stuff times itself 5 times. Which, when we multiply that all out and we count them out, we get x to the 15. So you don't necessarily have to remember the rule as long as you know what exponents do. So exponent means that you multiply this base by itself this many times. And all the stuff in the brackets you multiply by itself this many times. And when you do that, it's a longer way to do it, but it's really just counting up how many you have. It turns out that what you're doing is you're multiplying the 3 by the 5, right? So when you get an exponent of an exponent, when you divide, you're going to subtract the exponents. When you multiply, you're going to add the exponents. And even if you did it the long way, and so say like this x to the 2 times x to the 5, if I wrote that out, x squared is x times x times x to the 5 is x times x times x times x times x, which is x to the 7. Okay, so that's where those rules come from. It's not like a magic rule or anything like that. It's just a shorthand way of doing that instead of writing everything out. Okay. No, no, I'm saying one of those is right. I'm gonna let you pick which one. Yeah, because D, if you work that out, like 4 to the 6 divided by 4 to the 3, our rule is that we subtract the exponents, and the answer is going to be 4 to the 3. So that's got to be wrong. Yeah. No problem. So that was number 17. Now back here, next page. All right. And I'll paste it here. All right, so we've got, so this is one that's like what we're doing now, right? Like converting to a mixed radical or vice versa in simplest form. That means taking everything out of the radical that we can. Okay, so any part of that root of 27 that we can take out, that's going to make it simpler. Right? We want to reduce it down just like we would a fraction. And so I'm not going to do this one because you can solve that one. I'll do it with a different radical, and we'll say the root of we'll say 48. Okay, and so the way that we did this, there's a whole bunch of different ways you can do it, but basically we want to be able to turn 48 into chunks where at least part of the chunks we can do the square root of. So we need to take out something that is square rootable. Okay? And so the easiest way to do that, I find, is to find the prime factors. And so where we break up the 48 into numbers, like multiplication of numbers that can't get divided any smaller. So 2s and 3s and 5s and stuff like that. And if we think of 48, 48 is equal to 2 times 24, and 24 is 2 times 12, and 12 is 2 times 6, and 6 is 2 times 3. So right, 2 times 2 is 4, 8, 16, 16 times 3 is 48. So these are equal to each other. When I look here, I'm looking for things that I can take the square root of. And I know anytime I have a pair of a number, when I multiply them, it gives me a number that I can take the square root. And whenever I say that, it always comes out sounding like something that doesn't make sense. But let me try and boil it down, I guess. So if I took 2 times 2, I get 4. And I know the square root of 4. Square root of 4 is 2. And so I can it's like I can turn, I got an eraser somewhere here. It's like I can break this up. And this part here is square root of, well, this might be an actually better way to do this. It might look more clear. This here is 2 times 2, which is 4. Right? Square root of 4 times square root of 4 times square root of 3. Like, you see that there? Like, this is square root of 4, this is square root of 4, this is square root of 3. You all follow how I got to this? Yeah. This might be a better visual for how it works out rather than dragging the stuff through the, you know, how I kind of said it was like a machine. This might actually be a better visual for it, because it is like this square root of 4 times square root of 4 times square root of 3 is the same thing. And this, if I take the square root of 4, I get 2. Square root of 4 is 2. Square root of 3 is square root of 3. Well, 2 times 2 is 4. So it's 4 times the square root of 3. I've never done it that way, but actually that it kind of helps me see it a different way there. I don't know if that helps anyone else that was having troubles with it. Hopefully so. And so that's what we're doing. We're breaking it up into all its prime factors. We're trying to find pairs, because remember, for a radical that has nothing in there, our index is 2. So that means that it's like a square root. If it had been a 3, we need to have sets of 3. If it's 4, we need sets of 4. Any questions with that? Yeah. So let's see here. Yeah, so it doesn't matter what the number, like the number inside could be like a bazillion digits, right? And it would take a really long time, but we would do the same steps, right? Like break it down to its prime factors. So regardless of what's inside there, we're breaking it down. It could even have variables in there, like it could be like, say it was 32x squared or something like that. That's fine too, because we can treat the x like it's a number, right? And so this would be 32 is 2 times 16. 16 is 2 times 8. 8 is 2 times 4. There's 2 times 2. X squared is x times x. Right? And so in this here, if we break it up into pairs, we got this part here, which is the square root of 4 times the square root of 4 times this here will be the square root of 2 times the square root of x times x is x squared. And so we get 2 times 2 times square root of 2 times the square root of x squared is going to be x. Okay. So square root of 2. All this other stuff is on the outside. We have 2 times 2 is 4 times x times square root of 2. So it seems a little trickier, but it's the same process every time. Doesn't matter what's in there. And it doesn't matter if there's a number out there or outside already. It's just another thing that when we rearrange stuff, it's just going to be multiplied by the other stuff that's outside. And with this stuff, anytime you have questions, yeah, make sure you bring it up here. And if there is issues on the assignments and that, like I can be available to do a quick Zoom call or whatever, because like most of the time when I'm not in class, I don't really have that much going on during the day, and I'm fairly flexible with my time. All right.
I have a question.
Yep. The what?
Or where does that, how does the x go? 4.
Well, because we have 2 times 2 is 4. You're asking how this 4 gets here? Or
No, the x had, you just rearrange it?
yeah, because it's multiplication, I can put them in whatever order I want, and so the root 2 is the only one that's inside of a radical, so all the other stuff can be combined, and we would want to write it in that order, right? Like all the stuff inside the radical together, and then the stuff outside together. So we wouldn't want to write it like 4 root 2x. Like it wouldn't be reduced. Like technically, it's got all the stuff there, but it's not a. That wouldn't be as well. Do you know what? I would accept that, because this here is a number, and it's telling us we have this many x. So yeah, that would be fine. But yeah, you could you can either pull it to the front, or you could leave that x, because yeah, these are like numbers and this is a variable. So yeah, that's all good like this. Actually, do you know what? That's probably better to be like that, now that I think of it. It would make more sense that way. Yeah, it does. To me, looking at it now, it makes more sense to write it that way than to write it this way. This way looks weird to me now. So thanks for pointing that out, because that, no, like that actually does look way better. But I I would have accepted either one, just because I wasn't really thinking about. But if you think of it, like usually we want all the number stuff together, and then our variables, and so it would make more sense to do it this way. But either way, I would accept. Let's see here. All right, so I need a snippet. So this one, question 21, says when factored completely, the factors 5x squared minus 7x minus 6 are, and then it gives you some choices. Say you forgot how to factor something like that. What you could do is you could just take each of these, and you could actually work it out. Like you could do the 5x squared minus 15x plus 2x minus 6. This ends up being 5x squared minus 13x minus 6. That's not right. Okay, so we know that one's not right. So you could do it that way, or if you remember how to do the factoring, this one's a little bit tricky because it's got the 5 in the front, and I probably wouldn't it's a little bit trickier to find out. So this one's probably easier to do it like the backwards way, like by calculating these out and seeing which one comes out to that. But if it was a easier one, like so say it was like x squared, we'll say plus x minus 12. Let me just make sure in my head that that's going to work out. I think it does. So this type of question, or this type of polynomial, we can break it down because we've got the rules about, because what's going to happen when we FOIL everything out, this number that's in front of this is going to be the addition of this and this part. This one's going to be the answer when we multiply. So what's going to happen is we're going to get something that looks like x plus or minus something times x plus or minus something. Okay. And so if we look at this, our numbers that go in here are going to have to add up to 1. And we're going to have to multiply to negative 12. Okay. So the numbers that go here and here. So we need two whole numbers. They can be positive or negative, that when we multiply them, they come out to negative 12. And when we add them together, we get 1. And so the easiest way to do this, we start thinking, well, what goes into negative 12? Or even what goes into 12? And we got 12 and 1. And this just means one of them is going to have to be negative, right? For the answer to come out to negative 12. We have 6 and 2. And we have 4 and 3. Okay. So some combination of either 12 and 1, 6 and 2, and 4 and 3 can add up to 1, and it can multiply to negative 12. Okay. Does anybody see which set it would have to be? Well, so say we made the 2 negative, and we add those together. We're going to get 6 plus a negative 2. So count up to 6, then count backwards 2. We're going to get 4 as an answer. Okay, so it can't be that because our answer has to come out to 1. There's a 1 here, right? So 12 plus negative 1 is going to be 11. 4 plus a negative 3 is going to be what? So if we count to 4 and then we count backwards 3, we're going to be at that's what we want as an answer. So that means that one of these has to be 4 and the other one has to be negative 3. Because when we multiply 4 times negative 3, we get negative 12. And when we add them together, we get 1. So there's only going to be 2 numbers that work for it to come out this way. And so that's what we're doing when we're factoring. And it's that for this type of question, it's the one type that usually will work where these 2 numbers here are going to add up to this one and I'm going to multiply to this one. And so our answer for this particular one ends up being x plus 4 and x minus 3. This, when we work it out, comes out to x squared plus x minus 12. Okay, so we just factored it down to its parts. The other one, and we'll cover this more when we get into stuff where we need it, but there was a different one which was like difference of squares. So we had like, say it was like x squared minus 49, and we wanted to factor that. Anytime you have 2 things that are perfect squares and they're subtracted, the things that make that up are always going to be x. Well, we take the square root of this and the square root of this, so x plus 7 times x minus 7 will give us this answer. And that was another one that we learned that we needed to memorize. And those are really the only 2 that come up commonly, but we'll cover that in more detail when we get into that stuff in the chapters. Okay. But on the multiple choice test, you can just do like reverse, because if it's saying what are the factors, well, I can just multiply these out, and the one that comes out to this answer is going to be right. Okay, so I can always solve like different ways like that. just going to move on from that one. Let's see. We're getting close to the end. So this could be, okay. So this one here, I'm just gonna see if I'm not sure if I can make it small enough. So I think I have to copy it into. So this one here, it says the equation of the, we want a line that has the equation y is equal to 1 over 5 x plus 2, okay? And so in Math 10C, we learn about linear relationships. So when you have a straight line relationship between things, so when you graph them, you get a line that's straight. It's called a linear relationship. And those can always be represented by the equation y is equal to mx plus b, where m is the slope of the line, so how steep it is. So the bigger that number, the more it's increasing every time you go over 1, and so it's going to be steeper. B tells us the y-intercept. So if you add a number to your answer, it's going to move it up higher than it would be if this was 0, right? Or lower. If it was a negative number, it's going to move the graph down. And so our y-intercept, if you notice on this one, or these ones, y-intercept is where it goes through the y-axis. And on this one here, it looks like it is 2. On this one here, it's negative 2. This one here, it's negative 2. And this one is 2, right? And so if we're trying to figure out what the equation of each of these graphs are, that number is going to be the part that is that number is going to be the part right here. So if it's a negative number, you'll get subtract that number. Positive number, it's going to be add that number. M is the slope, which the slope is just the rise over the run. So it's how much it increases divided by how much it moves to the right. Okay? And so this here, this slope of 1 over 5, means it goes up 1 every time it goes 5 to the right. So it'll go 5 right, up 1, 5 right, up 1. And so we would be able to look at this and go, well, which one is, well, we can rule out certain ones. Like if it's going down, it has to have a negative slope. So we always look at it how it goes from the left to right. So this particular one is going down, and it's going down 1 every 5. So it has a slope of negative 1/5. This one here has a slope of negative 1/5. These two both have a slope of 1/5, but only one of these two can be right. Because the one that, because it's y-intercept, one of them is going to be positive, it'll be plus 2, and the other one's going to be subtract 2. Okay? And so this, when we do our graphing unit, there's not that much in Math 20 with it, but there's a lot more in Math 30. So it'll be stuff we cover. But yeah, so basically, anytime we see a straight line, we know it's going to be in this format. We're looking for a slope that matches what it says. So this one says 1/5. That's a very shallow slope. It's not very steep at all. A number like 5, it's going to make it tilted up and be steeper until eventually, like a vertical line is going to have a really like it's basically infinity would be the number for the slope. And so in this one you should be able to pick out which it is. I'll do a quick one here. And so I'll say y is equal to 5x plus 1. And basically what we can look at is on the graph, like the simplest version of this, the mx plus b, would be where m is 1, and so I just leave it as x, and b is 0. And so all these line or linear graphs are going to be we call transformation of y is equal to x. Right? And y is equal to x is just like the line that's on the diagonal like this. Right? So if this is 1, this is going to be 1. And this is 2. This is going to be 2. If I put a number in front that's bigger than 1, so say there's a 2 in front, all of a sudden at 1 this is going to be 2. At 2 it's going to be 4. And at 3 it's going to be 6, and so on. And it's going to be steeper, and we're going to get a different slope. Right? Like this would be the one that would be like y is equal to 2x. Would be y is equal to x. 5x is going to be even steeper, because at 1 your answer is going to be 5. Right? This plus 1 is going to move everything up 1 block. So even when you're at 0, 5 times 0 is 0 plus 1. That means it's going to come through here. At 1, it's going to be 5 times 1, which is 5, plus 1, which is 6. It's going to sound right up here. Okay, so you're going to end up something like that. So we need to be comfortable looking at a graph and be able to say, well, what would be the equation of that graph, or how would I find that out? All I need to know is the y-intercept, and that's going to give us this number, and I need to know the slope. That's going to give us this number. Otherwise, it's the same process every time. If it's a curved line, you can't do straight lines. Yeah. That makes sense. Should be good to do that question now. You all still hear me? Okay. I think it's the last one that's on here. Well, this was just checking your how you think your math ability is after doing those. So the idea here, you'll be able to see what you picked. You'll be able to see what your confidence level was. The ideal scenario here is that you go through and do it again. When you go and you look at a question, you got it right, check and see what whether you thought you knew it or not. And then if you're feeling like what I went over or talked about makes you feel better about it, change your answer on whether you're confident in doing that type of question or not. When you get to one that you got wrong, check again, because if you thought you knew what you were doing and you got it wrong, that's something maybe to make a little note of. And so the stuff that you got wrong, it would probably be a good idea to have a sheet of paper out that you're going to make a little note on, that was something you needed to freshen up. And then you would be able to go back to the video and watch it if you need to, or if you can do it right now without going back to the video, that's great. You go through, check it again, and then we keep doing that until there's none left on there that you need to figure out. Don't just go. Sorry?
So the questions that I got wrong and stuff, I could just like YouTube it and stuff like to refresh my brain.
No. I went over all the questions here.
Okay. And
So
then you're gonna post the video?
yeah, but what I would do now that you got like a little refresher on everything, go through every question. We want to get to where every question is going to look like say on this one, say I had picked the wrong answer and I didn't feel comfortable with it or whatever. I would want to try it again, because I've gone through every one of these questions, right? So try and do it again based on what you remember from what I went over, and put down whether you feel confident of it or not. Go through and do that. You'll only have to change the questions that you got wrong, because I found the setting to where it will leave your correct answers there, and you only need to go in and change them, and you can keep going in and doing that until you get them all. I know, like, in theory, a person could just go and guess, and it would take, you could guess everyone, and 4 times through you're going to get them all right. But the idea would be to get where you can do them and you're fairly comfortable with them. And so yeah, if you can go through and do them, try and do the ones that you got wrong with what you've learned just in these couple lessons. The stuff that's left over after that, those are the things that we'd want to, maybe watch a YouTube video or check with me or some other way to find that, to close that gap, right? But what's nice with this is, if I asked you ahead of time which of this stuff you probably got a bunch right that you didn't think you really knew, and so you would have been going and learning stuff you didn't really need to learn. And so it helps us focus on the stuff that's actually gaps, right? And so it ends up taking way less time than going over all these topics in detail. And it also should help with your confidence to realizing, okay, I knew more stuff than I thought I knew, right? And so yeah, that's the process. And so what I'll do is I'll keep the Zoom call open for now, yeah, you can use the rest of the class to go and do those questions. I would still go through and do them again without stopping and looking stuff up, because you're going to have some more stuff because I have gone through all the questions here, you're going to have more stuff that you probably are going to be able to pull out of your brain. Whereas if you think maybe you don't know, and then you go and you look up a bunch of stuff, it ends up not being a good use of your time, right? Because if you can draw it out of what you got in your head, then that's the best thing, right? And then the stuff that's left over after, that's the stuff we'll go in and make a little plan for how to get that stuff cleaned up. Make sense? Let's see. Am I still sharing the screen? I'm going to stop this recording here.